Hello everyone, this is lecture 45 of PEC. In lecture 25, we have introduced how to constitute the gate circuits with MOSFETs. In this lecture, we will introduce how to constitute the amplifier with MOSFETs. Gate circuits and amplifiers are the basic units of the digital system and analog system respectively. They are the core components of the signal processing. In the following lectures, we will introduce how to deal with the energy by using MOSFETs. Let's get started. Before the discussion of the amplifier circuit, let's recall three different working regions of the MOSFET and their constraints. First, G and DS of the MOSFET is always open. Secondly, when UGS is smaller than UT, there is an open circuit between D and S. When UGS is greater than UT, there might be the current flowing through D and S. We can draw it like this. It can be roughly divided into this section and this section. In this section, UDS is relatively small. That is to say, if UDS is smaller than UGS minus UT between D and S, it can be regarded as a linear resistor. While in this section, UDS is relatively large. That is to say, if UDS is greater than UGS minus UT, it can be seen as a voltage-controlled current source between D and S. This controlled quantity, IDS, equals K times UGS minus UT squared over 2. Now, you can find that it is a nonlinear voltage-controlled current source. In lecture 24 to 26, we have discussed how to constitute the gate circuits by using the open circuit and the resistive characteristic of MOSFETs. In this lecture, we will discuss how to constitute the amplifiers by using the voltage-controlled current source characteristic of MOSFETs. Okay, we will take an example to discuss the analysis of the amplifier circuits constituted by MOSFETs. The topology structure of the circuit is the same as the inverter circuit. If the MOSFET works as a nonlinear voltage-controlled current source between D and S, then the circuit is a nonlinear resistor circuit. We can use the small signal method discussed in the previous two lectures to analyze it. Of course, the premise is that delta UIT can be regarded as a small signal. Now we use the suppose verify method discussed previously to judge whether the MOSFET works in the current source region or not. We can first assume that it works in the current source region. Now we need to draw its DC working point circuit. That is it. For such a circuit, the output is UDS. In order to find UDS, we need to use the KVL. In such a path, we can get that it is equal to that is 4.375 volts. According to the previous review, we know that the condition of the MOSFET working in the VCCS region is that UDS is greater than UGS minus UT. It is 4.375 in this problem. It is 2.5 minus 1 equals 1.5. So it is true. So we verified that the MOSFET works in the nonlinear VCCS region. And we know the working point UDS equals 4.375 volts and the UGS equals 2.5 volts. Next, we will use this condition to draw the small signal circuit of the nonlinear resistor circuit. In the small signal circuit, all the DC values are 0, so the input contains only the small signal. The output is between D and S. Here, the nonlinear VCCS is changed into a linear VCCS. Its characteristic is like this. In this circuit, in order to find delta UOT, we need to use the KVL in this path. Thus, we can find from this formula. This MOSFET amplifier amplifies the input signal with minus 7.5 times. That is to say, from the AC signal perspective, the ratio between the output and the input is 7.5. In order to complete the analysis for the whole circuit, now we need to write the DC part and the AC part together. We finish the small signal analysis of the amplifier circuit containing the MOSFET. Here, I need to remind everyone that in the small signal MOSFET amplifier circuit, the input and output are the common source configuration. So the amplifier is also called as a common source MOSFET amplifier. In the future courses, you will also meet other types of the amplifiers. Next, we use a simulation and an experiment to verify the theoretical analysis. We now verify the function of the MOSFET amplifier circuit by the simulation. In the figure, the MOSFET is 2N7000. 10 volts source and a 10K ohm resistor are connected between D and S. The input signal is connected between G and S. The input signal includes DC 2.05 volts, a sine voltage source with 1 millivolt RMS and 50 Hz. The 2.05 volt DC ensures that MOSFET works in the VCCS area so that it has an amplification function. Channel A connects to the input, expressed by the red line. Channel B connects to the output, expressed by the green line. Open the oscilloscope, click Run, and then pause. We use the AC mode to observe the waveform. The red line is the input AC signal. The green line is output AC signal. The input signal is 1 millivolt per division, and the output signal is 50 milliwatts per division. The output signal is roughly amplified minus 50 times of the input signal. The function of the signal amplification has been realized. Now we understand the performance of a MOSFET amplifier. The input is a superposition of a DC bias and an AC small signal. The AC small signal connects to one input terminal of the emitter. The potentiometer is used to adjust the DC bias. It connects to another input terminal of the emitter through a voltage follower. Through an emitter and an inverse proportional amplifier, the ended signal is the input of the MOSFET amplifier. We observe the AC small signal and the output of the MOSFET amplifier by the oscilloscope. Now let's look at the waveforms. Channel 1 is the AC small signal with DC bias. Its peak-to-peak value is 0.2 volts. Channel 2 is the output of the amplifier with DC bias. It can be seen that the alternating part peak-to-peak value of the output waveform is about 6.4 volts. That is to say, the small signal is amplified over 30 times. It shows that the circuit realizes the function of the amplification.